Next, we're going to talk about induction. So induction, or mathematical induction, is a proof technique which allows us to prove that a statement is true for the entire set of natural numbers. So it's a proof technique that allows us to prove some statement S sub n for all n in a set of natural numbers. Sometimes this could be extended a little bit. Maybe it's the all integers greater than or equal to 0. So we could include 0 or not include 0. Maybe it's just all natural numbers starting 2 or higher. But in general, it's going to be this set that's similar to the natural numbers. So we can prove all sorts of different statements this way, as long as that statement needs to be true for some set or subset of the natural numbers. So I've got 3 examples here. So we could show that given a natural number n, the sum of the first n integers is n times n plus 1 over 2. It's a very classic first induction proof. We can prove things about inequalities. So in the inequality, 2 to the n is less than or equal to 2 to the n plus 1 minus 2 to the n minus 1 minus 1. And that holds for each n and n. Or we can prove other statements that just have to do with arbitrary n's where that n is a natural number or a positive or non-negative integer. So for example, this one is about a tree, and we'll talk about what a tree is. It's a special type of graph. So a tree has n vertices, then it has n minus 1 edges. So again, that has to be true for every natural number n. Therefore, that's going to be something that we can prove with induction. So to get the idea behind induction here, we want to get some intuition for what's going on. So the way I think about it is the following. I'm going to have this bag here, and the bag has some numbers in it. So for example, the number 1, let's draw a nice 1 here, is in this bag, right? So I have this number 1, and I'm going to put that number 1 inside my bag. And then I'm going to put some other numbers into my bag. So I don't know what numbers they are. I'm not going to necessarily tell you, but I'm going to put a whole bunch of numbers in the bag. And then when I'm done, I'm going to tell you 2 facts about the numbers in that bag. So as we can see, the number 1 is in the bag. And then the second fact is, for every number in the bag, that number plus 1 is also in the bag. Okay. And then the question is, which numbers are in the bag? So I'll give you a second to think about this. Okay, so I know that this number 1 is in the bag because that was given. Since 1 is in the bag, the next number must be in the bag, so 2 must be in there. But now since 2 is in there, 2 plus 1 must be in the bag, so 3 must be in there. 3 is in there, so 4 must be in there. 4 is in there, so 5 must be in there. 5 is in there, so 6 must be in there. Right, so we keep building up and up and up. And we know for every number we get one more number. We're going to get every single integer, positive integer. So really, the numbers in the bag is the set of natural numbers. So all of those natural numbers. So this is the idea that we want to extend into a proof technique here. So when I'm trying to prove something is true, if I can prove that it's true for 1, and I can prove for every number it's true for, then it's true for the next number, then it should be true for all natural numbers n. And that's how induction works. So before we move on, I want to see if we can just rewrite this second fact here as an if-then. Right now it says for every n, if the statement is true, so let's say B sub n means n is in the bag. That means that B sub n plus 1 is in the bag. So the second statement here is really saying if the statement is true for something, so if a number is in the bag, then the second number is also in the bag. And that's what we want to have as part of this proof technique. So let's go through and just write down this idea of induction. So given an open sentence, P sub n, right, so that's some statement that has some variable that could be a natural number. To show that for all natural numbers n, P sub n is true, we want to show that P sub 1 is true. We want to show that it's true for the first statement. And then we want to show that P sub k implies P sub k plus 1. So for every statement it's true for, it has to be true for the next statement as well. And then it has to be true for every statement. So these are the two big things that we have to show. They have special names, so let's go ahead and name them here. So when I show that P sub 1 is true, that's called the base case, or sometimes the basis statement or the basis step. That's the terminology the book uses, but I'm going to call it the base case. And then when we prove P sub k implies P sub k plus 1, that's called the inductive step. Now, when we're proving this implication, in order to do that, we're going to assume P sub k is true, and then we're going to show P sub k plus 1 is true. When I assume P sub k, that's called my inductive hypothesis. So it's going to be kind of weird because it's going to look like we're assuming what we're trying to prove. So I specifically changed the letter to K there instead of N, so it looks a little bit different. But remember, this is just part of the proving that conditional statement as part of our induction step. Because I need to prove this if-then, I need to assume the if and then show the then. Again, so another way to think about this is to think about it as sort of dominoes. So we have all of these dominoes set up here. When we show P sub 1 is true, it's like hitting over that first domino. And when we show that P sub k implies P sub k plus 1, it's like saying that each domino will hit the next domino. And then I know that every single domino will fall. So we can think of that as sort of another way, another intuitive idea of how these inductive proofs work. Let's see an example of what an inductive proof will look like. So here we're asked to show that the sum from k equals 1 to n of k is equal to n times n plus 1 over 2. So if you're not familiar with this notation here, right, big sigma stands for sum, so I'm adding things up, starting with k equals 1, so I get 1 plus 2 plus, and I keep going all the way to n. So I want to show that that sum, when I add from numbers 1 up to n, gives me n times n plus 1 over 2. So maybe this is a formula you've seen before and worked with before. So let's go ahead and actually prove it. So whenever I'm starting an inductive proof, we want to tell the reader what we're going to be doing. So usually we say something like, we proceed via induction. And sometimes you say what you're going to induct on if it's not going to be clear. So here we could just say induction on n, or we could just leave that off. And then the first thing that I need to do is do my base case, or my basis step. So I always like to actually write that out. The base case is the starting point. So here I want to show this for n greater than or equal to 1. It's sort of implied there that n is a natural number. So I could have also said for n in n. So the starting point for my n is n equals 1. So I can say let n equals 1. And now the big thing that I have to be careful about here, what I don't want to do is just plug n into both sides. So we'll put a little warning. Don't plug n in with that equals sign still there, right? Because I don't know that they're equal. That's what I'm trying to show. So I can't just write, oh, sum k equals 1 to 1 of k equals 1 times 2 over 1, because I don't know if that's equal yet. So it's better to actually work with both sides separately and then put them together. So what do I mean by that? So I'm going to say on the left-hand side, so you can use that abbreviation if you want, we get the sum from k equals 1 to 1 of k, which is just 1, because it's 1, not added anything, there's only one term. And then I'll say what it looks like on the other side as well. On the right-hand side, we get 1 times 2 over 2, which is equal to 1. Since they're equal, the base case holds. So I showed that my two sides were equal by first figuring out what they were both equal to and then stating that those were equal to each other. After we do that, then we can do our inductive step. Our inductive step is when we prove that, so just one step, not steps. So what am I going to do here? I'm going to prove that the sum from k equals 1 to n of k equaling n times n plus 1, that implies that the sum from k equals 1 to n plus 1 of k equals n plus 1, n plus 2 over n. So I need to try to prove this implication here. So to prove an implication, I'm going to assume the if. So I'll assume that, let me change colors here because pink is sort of the stuff that I don't really need to write as part of my proof. So I'm going to assume the sum from k equals 1 to n of k equals n times n plus 1 over 2. Now here it's a little strange, right? I said before in the previous slide that usually when we do these assumptions, we're going to replace that n with a k. I already used k in this problem to mean something else, so I left it as an n instead, and that's fine. We'll see lots of examples where we use different letters here. But it does seem very strange because I literally just assumed what I was trying to show. But we have to remember that that's okay because we're assuming it as part of our hypothesis to prove this if-then. So this is my inductive hypothesis. So we don't have to write that. It's sort of known that this is what that thing is called. But when I refer back to it, I can refer to it as my inductive hypothesis if I want to. Okay, so I'm assuming my if, and now I need to show that the sum from k equals 1 to n plus 1 of k is equal to this. So again, I can't just start with what I'm trying to show here, but I can start with the one side of it. So then the sum from k equals 1 to n plus 1 of k, I'm only going to write for sure what I know what that's equal to. Now, if you're not comfortable with this notation, remember that this is just going to be 1 plus 2 plus all the way up to n plus 1. And now I know that these first n terms, by my inductive hypothesis, that's just n times n plus 1 over 2. So then that's just n times n plus 1 over 2 plus n plus 1, and then hopefully we can do some algebra to make that look like what I want to show. So let's go ahead and see if we can put this together. I'm going to do it in this summation notation still. So I'm going to first just write the first n terms. So that's just adding up 1 through n. And then after that, I can add my n plus first term. So I'm just rewriting my summation notation here. And then that's equal to, well, I assumed that this quantity was equal to n times n plus 1 over 2. And then I'm adding on that n plus 1 over there. Sorry, that n plus 1, I wrote 2. Let's fix that. By my inductive hypothesis. Now, I'm going to be a little sneaky with my algebra. You could multiply everything out, get a common denominator, all that stuff. But I've done this problem thousands of times, so I know that the best trick is to notice that they both have an n plus 1 as a common factor. So I'm actually going to factor out that n plus 1. And I'm left with n over 2 plus 1, which is n plus 1 times, now I get a common denominator, n plus 2 over 2, which is what I wanted to show. So just kind of notice that's what I wanted to show. Thus, by induction, since I proved that P sub 1 was true, the statement was true when n equals 1, and I showed that for any n that it's true for n plus 1, we can conclude that for all n in the set of natural numbers, the sum from k equals 1 to n of k is equal to n times n plus 1 over 2. So I encourage you to take a minute, pause the video, go back, read through this one more time, and see if you can think about where all of these things come from. And when you're done with that, think about why we've actually proved something here. Why is this statement true for n equals 5, for example? Why is it true for n equals 10? How does that proof actually work? We'll finish this video with the discussion question. So if P of 1 is true, and for all n, P of n implies P of n plus 1, right? So that's what we prove in an inductive proof. Given that, why is it true that P of 5, for example, is true? So really think through how this induction works.